Hello everyone, this is Dad Engineer Guy. Welcome to the last lecture of Special Theory of Relativity. In this lecture, we are going to talk about Doppler Effect. We are going to talk about astronomical Doppler Effect. We will talk about the dynamics that is related to relativity in general, that is your momentum expression, the kinetic energy expression and all that. So let's start from Doppler effects. For those of you who don't know what is Doppler effect, I will explain it in brief. Let's say there is a source. Now, whatever I am talking about the Doppler effect, it is applicable only for waves. Waves as in transverse waves. So transverse wave, sound is a transverse wave, light is a transverse wave, sound is a this wave, sorry. ये क्या है ये गादी गादी हटाई रोहन में ना गादी लगा के रखता है हमेशा starting from here. So now let's talk about Doppler effect. So for those of you who don't know what is Doppler effect, I would say that I would explain it in brief. So Doppler effect is a phenomenon that is observed in all kinds of waves, transverse as well as longitudinal. So what you will observe that basically, let's say I am defining Doppler effect for sound. So sound is a wave, as all of us know. So let's say this is a source of sound and it is moving with some velocity, and there is an observer which is recording the frequency of the source, frequency of sound that the source is emitting. Let's say that is f. So now, according to general common sense, we would say that if they are not moving relative with each other, that means there is no relative motion existing between the observer and the source, then no Doppler effect is observed. Or in general, the frequency recorded by the observer of the sound of source would be the same. That is, if f is the source, is the frequency of the sound that the source is emitting, then observer will also observe f if there is no relative motion existing. But if relative motion exists, then Doppler effect says that the frequency would be less or more as compared to the original frequency of the source. So how is that term given? So let's say the observer records a frequency f naught and the source has a frequency f. Then the expression for Doppler effect is given to f naught Vg plus minus V naught upon Vg plus minus Vs. Now I'll explain what is Vg, what is why have I used plus minus, why have I used what is Vs and all that. So basically, what you know, f is basically original frequency of source. I'm assuming you know what is frequency. Frequency is basically the number of crest and trough that we follow in a wave, right? So f is the original frequency of source. F naught is the observed frequency. And now let's talk about this bracket. So Vg is basically the speed of the wave. Now which kind of wave I am talking about? Right now we are talking about sound waves, but Doppler effect can also work for light waves. That's why I am going to then take it up as a case of light waves. So first we'll talk about sound waves, so speed of wave. So in this case it is sound, so I'll write sound, right? And you know the speed of sound, if the medium is air, then the speed of sound becomes approximately 330 meters per second, right? This is the standard value. V naught is the velocity of observer, or rather the speed of the observer. V naught is the speed of the observer, and Vs is speed of source, right? So there will be some time when observer is at rest but source is moving, so at that time the V naught term becomes 0. There will be time when both of them are moving, so we have to add it accordingly. So what is the reason behind plus minus and plus minus? So basically you might have learned this in your elementary classes in mathematics, that if you want to increase a fraction, then you have to increase the numerator, or you have to decrease the denominator, and you have to increase the numerator and decrease the denominator if you want the overall fraction to increase. So if let's say a train is coming towards me and I am observing the train that it is coming towards me, and I am trying to record the sound of the whistle that the train is blowing. So the whistle will have more frequency as compared to that which is its original. because it is coming towards me, so I will get more sound waves excited to my ear, and because of that the frequency observed would be more. So if I want to make the f0 term greater than the f term, that means I have to increase the numerator and decrease the denominator. So for numerator, I have to add the plus sign. Since the numerator will increase, if I add a plus sign, if I add minus sign, then the numerator will decrease, right? That won't make sense. So if I want to increase the f0 term, I have to increase the plus sign and I have to decrease the minus sign. Decrease the denominator, so add the minus sign in the denominator. So this is how it works. Same can be applied to the principle of light. Now, how can we apply this whole Doppler effect to light waves? So, Doppler effect for light. Now, first of all, there is a question why Doppler effect is applied for light. So, of course, we know light is a wave, so Doppler effect can be applied to light. But why, like in sound, we can observe the frequency to be greater or we can observe it to be less of the source, right? So, observer can, if the source is moving towards him, the frequency will be more. If the source is moving away from the observer, then the frequency will be less. How can we infer this in the case of light? So, in light, the same thing will apply. Frequency of the light source will be greater if the source is approaching towards the observer, and consequently the wavelength will be less. And if the wavelength will be less, so according to the visible spectra, we know that visible light exists from 4000 to 7000 angstroms, roughly approximately. So if the wavelength, if the frequency is increasing, that is the source is coming towards us, the wavelength will decrease. And which part of the visible spectrum has a lower wavelength? The violet color, right? So whatever, so if let's say there is a star that is coming towards us and it is emitting a source of light and we are trying to observe it with the help of a telescope, then the frequency of the star observed, frequency of the light source that the star emits observed will be more as compared to the original frequency of the star. Hence, the wavelength will be less because frequency and wavelength are inversely proportional to each other. So the wavelength will be less and we will observe the star to be somewhat violetish or bluish. So it is known as blue shift. I'll explain this now in depth. So we'll also obtain an expression consequently for the Doppler effect of light, just like we obtained it for the Doppler effects of sound. So assume there is a star that is moving away from you, let's say moving away from you, and you are on the earth at rest. The star is moving with velocity v. So what kind of color the star will emit? We have to calculate that. So let's say star is emitting a frequency f, right? It will emit it like this, but consequently it is also moving away. So the frequency will be less, that we know by intuition. Now let us calculate mathematically. So applying the Doppler effect for sound, we can apply it same for light. So f equal to the frequency that this guy observes is f0. So f0 Vg plus minus Vs, Vg plus minus V0 upon Vg plus minus Vs. Right? This is true for light also. Now Vg will be the speed of light, that is c. V0 will be 0. Vs will be V. Right? And now applying all this here. So f will be basically f0. Vg is c. Now since the star is moving away from us, the frequency should be less. So the denominator needs to be minus. The numerator should be minus. But doesn't matter because V0 is 0 anyway. So c minus 0 upon Vg. Vg is the speed of light. And since it is moving away, so that means the denominator needs to be increased. So plus Vs, that is V. This is basically f0 c upon c plus V equal to f0 c upon c plus V. Now I'll do an interesting thing. I will divide the numerator and denominator by c. So what I'll get? f0 1 upon c by c divided by c by c. So 1 plus V by c. And what is V by c? We know in light we have come across this term V by c, that is 1 upon 1 plus beta. Right? 1 upon 1 plus beta. Now I'll do another interesting term. Let me first mark this. Since any object in the universe is known to have speed less than the speed of light. There can be no object in the universe other than light which has the greatest speed. So that means v by c will be less than 1. You agree with this? Because v is less than c. So I take the c here. So v by c is less than 1. That means beta is less than 1. Now this term, can I write it like this? F naught 1 plus beta raised to power minus 1. I just took the denominator up, so I made it minus 1. Right? Now, if you have learned this thing called approximation, even if you have not learned, doesn't matter. Basically, it says that if I have 1 plus x raised to power some n, where x is less than 1, it is a very small quantity as compared to 1. So it is basically a decimal. And then it basically turns out into 1 minus x. 1 plus nx, sorry. 1 plus nx. 1 plus nx. So this power comes down in the bracket and becomes this. Right? You can look up this in the Google also. So now I formulate for this expression, I will write it in terms of this. So the final expression that I get will be f equal to f naught 1 plus beta raised to power minus 1. So basically 1 plus x raised to power n is 1 plus nx. So it becomes 1 minus beta. And this is your Doppler effect for light. So usually stars are moving away from us because the Milky Way is moving in one direction. So star is moving away from us. So if you are on the earth and you are moving ahead and the star is moving away from the earth, then you will observe the frequency to be this. Right? So this is about frequency. Now what can I tell about the color of the star? So if usually the star is of some color, it will appear to me that the star is violetish. So this phenomena where the star is moving away from us or the object is moving away from us, object is a light source, and if it is moving away from us, then the frequency of the star or the light source will be less as compared to observed, and the wavelength consequently will be more. So if the wavelength is more, that means which part of the visible spectra has a more wavelength. So visible spectra is 400 nanometer. Visible spectra is from 400 nanometer to 700 nanometer. 400 nanometer is violet and 700 nanometer is red. The highest wavelength, because red is, you can remember this with the help of an example. Red is used in traffic lights. Red is used in traffic signals. Why? Because when the signal turns red, then even the people who are, let's say it is a very crowdy area, and the vehicles which are at the back, even they need to see the signal, right? So in order for the red light to quickly excite the retina, the red should have most wavelength. You can remember it by this example. Red should have the highest wavelength and violet should have the least. So if by some process a star is going away from us, frequency recorded will be less, wavelength will be more. That means apparently the the color of the star that will be observed by us will be red. Phenomena by which a star moving away from the observer at rest is observed to be red. Observed to be somewhat red, I would say. Somewhat red. Because no star can be observed directly to be red, right? It will be increased in wavelength. The light source that you will observe, it will be increased in wavelength, and that's why it will appear somewhat red. So somewhat red. This is known as redshift. And consequently you have blue shift. Right? So blue shift is the opposite of this phenomena by which a star moving towards the observer at rest is observed to be somewhat blue because of the decrease in wavelength. Right? So this is basically red shift, blue shift, and this entire thing is Doppler effect for light. Let's talk about the dynamics involved in relativity. So what exactly I mean by the term dynamics? Dynamics deals with all the quantities or all the qualities that you have when the particle is doing motion. Right? all the qualities that you have when the particle is doing motion. So when the particle is doing motion, it is basically moving, right? So dynamics refers to movement. So in movement, we talk about momentum, we talk about kinetic energy, right? So according to classical physics, what do I define as momentum, or what is the mathematical expression for momentum according to classical physics? We say vectorically that momentum vector is the scalar multiple of velocity vector, right? So P equal to mv. P is the momentum, mass, velocity, right? So physics. There is also another formula which is the standard formula, and basically it is the second law of Newton, second law of motion stated by Newton, that force is the rate of change of momentum, right? d by dt is the derivative, P is the momentum vector, F is the force vector. So what this basically states that if force acting on the body is zero, let's say this term vanishes and it becomes zero. So what will be the momentum? It will be the integral of force dt. From here, momentum will be the integral of force vector with respect to time. Force becomes zero, the force vanishes, then this will turn to a constant c, because this will be zero, the integration of 0 is 0, and then you get a plus c, which is your whatever constant that you obtain after indefinite integration. So that means when force is 0, when force acting on a system is 0, force acting on a system is 0, momentum is conserved. Momentum is conserved. What do I mean by conserved? The initial momentum will be equal to the final momentum, right? So it will be a conserved quantity. Same is applicable to relativistic physics, that whenever the force acting on the system of the particles will be 0, then the momentum will be conserved. But now, if I take this mathematical expression and I compare it with relativistic physics, we know that in relativistic physics we are in all inertial frames, right? So in inertial frames or non-accelerated frames, if a frame is moving with some velocity, then the velocity will also be a changing factor, right? So in some inertial frame, let's say I am moving with 20 meters per second and I observe the system. The system is having momentum conserved. But if momentum is conserved, that means the velocity should not change, because mass, as stated by classical physics, mass is a constant quantity, right? No body can change its mass according to classical physics. So velocity is changing, mass should not change, but yet I am saying that momentum should remain conserved, because according to laws of physics, every law of physics is conserved in an inertial frame and even as in a rest frame. So even in a rest frame, you move with any velocity, the laws of physics should remain same. Momentum should be conserved. So velocity is changing, because in inertial frames your velocity keeps changing. You are moving with different velocities. Some person in another inertial frame may move with another velocity and observe the system. So velocity is changing. Mass, as stated by classical physics, is changing. But momentum should be conserved. Options here, right? Either I say that momentum is not conserved at all, which would be a big crime to say that momentum is not conserved whenever the force is 0, right? It is a big crime. Otherwise, I would say that this expression needs to be changed. So the second answer is correct. Then second answer is correct, that this expression is not correct. This expression is valid only for classical physics. In relativistic physics, this expression changes, and what basically happens is a very uncommon sense that you would say that the mass is the one that gets changed, right? So m equal to m naught upon gamma. What is m naught? What is m? M naught is rest mass, or if there is no velocity, then m naught is the rest mass, and m is the relativistic mass. So basically, when a body is moving, then the relativistic mass, then the mass of the body shrinks, is what I am trying to say here, right? This is what happens. I will try to prove it mathematically also. So let's say we are taking this expression, we are working with this expression only, and we want to derive a formula for the relativistic momentum. So let's say momentum is equal to, what is momentum basically? That is m times v vector. Can I write v vector as delta x upon delta t? Rate of change of position is velocity. Rate of change of position is velocity. Right? Now, the time interval that you are observing is changing, because the time interval is time is relative in relativistic mechanics, you know that, right? So let's say I am observing a particle which is moving with velocity v, and it is covering some displacement, or it is changing its position with the help of delta x, right? And I am an observer who is also moving along with him. So I have one clock in my hand. I am seeing that at t equal to 0, this guy is at this position, and at t equal to delta t naught, he is at this position. So I am moving along with him. I just have to carry one clock. That means I am in a proper time interval. So if I am in a proper time interval, I write this term as a proper time interval function. So it is basically delta t naught that I have to write here, right? Because momentum is conserved in all the reference frames. We know that. So equal to mass times delta x upon delta t naught. What is delta t naught? Delta t naught, or let's say delta t dash, equal to gamma times delta t naught. This is the time dilation equation. Delta t dash gamma times delta t naught. Time gets dilated. So from here delta t naught will be delta t dash by gamma upon gamma. So gamma goes in the numerator. So this basically becomes gamma times delta x upon delta t dash is your velocity vector. So momentum vector equal to gamma mv vector. So if I write them in scalar form, it will be P equal to gamma mv. And if you compare this expression with this expression also in the scalar form, let's say it is a scalar form, right? So if you compare this scalar form with this scalar form, you will find that these factors should be equal if they have to be equal, right? So these factors should be equal. That means here basically it is m naught, because I have defined the rest mass, right? So in classical physics there is only rest mass. Mass does not change. So gamma m equal to m naught implies m is basically m naught by gamma. That means the mass of a particle changes. And if you think about it in deeper way, you will also say that yes, it should change, because if length is contracting, that means mass also somewhat has to contract. You can think of it like that. So if if length has to contract, mass also has to contract. So yes, mass changes, and if I try to write it more specifically, it will be m equal to m naught under root of 1 minus v square by c square. Right? So this is how it works. Since we talked about momentum, now the next topic we go on to is energy. So there is this one energy which you all may be familiar of, that is known as mass energy. Right, so what happens basically is that if you have a certain amount of mass that is changing, that is, you have a mass, your mass is decreasing, then that equivalent amount of mass is equivalent to a certain amount of energy, right? Now this is not quite applicable in day-to-day life, because when we are, let's say we are losing some mass, then the mass lost is very less as compared to our original mass, right? So if let's say I'm 80 kg, if I am 80 kilograms and I am losing some mass, then the mass will be of 0.04 microgram, something like that. So it is very less as compared to my original mass. So as we know that mass is changing, as we came across earlier, that rest mass decreases, right? So mass, as you are moving with speed v, the mass will decrease as compared to the rest mass. So that means, where has the mass gone? There it is a question that where has the mass gone? So mass has basically changed, or equivalent, or it has become equivalent to a certain amount of energy. And that expression is a very famous expression which you all might have come across. This expression, E equal to mc square. Very famous expression. But problem is that some people confuse this with the mass. It is not the mass, it is basically the change in mass. Change in mass. E equal to delta mc square is the correct term for change in mass. This is the mass energy. See, this term is not more used in our lower grades because it is not a day-to-day phenomena that you will observe. In chemical reactions, the mass loss is very less as compared to the original mass of the substance. So because of that, this cannot be applied everywhere, right? So where can it be applied? It can be applied in nuclear reactions. In nuclear reactions, what happens? The mass of the substance itself is very less, right? So it is in AMU, atomic mass units. So since it is in AMU and not in kilograms or grams, and the mass change becomes significant then. Because of that, the mass change becomes significant, and because of that, this can be applied more in nuclear reactions. So let's say I am considering a nuclear reaction is happening. So this is basically the parent nuclei, as you would say, parent nuclei, and it is getting converted by some of the other reaction into daughter nuclei, right? It can be many, not just two daughter nuclei. So it is getting converted into daughter nuclei. What is happening? Can I write the energy equation for this thing? So I can write the total energy of the system. The total energy of this system will be the sum of its kinetic energies plus the sum of its potential energies plus the sum of its mass energies, because mass is also getting converted. So mass energies, right? Let me write it as E only. Now what we usually do, we assume that this is a reference level where potential is zero. Reference level where potential is V. Potential is basically zero. If potential becomes zero, we do not consider the potential energy. So we make it zero. From here we can calculate the kinetic energy expression. Right? We can talk about the kinetic energy expression. So from here Ek will be total energy minus mass energy. Now the total energy is found out to be gamma mc square. Right? E total is found out to be gamma mc square. What is my mass change? That is delta m c square. So delta m I can write it as m. So m c square. So basically your kinetic energy expression becomes gamma minus 1 m c square, and this is your relativistic kinetic energy, right? So your classical kinetic energy, where the speed of the object is not close to the speed of light, that is basically half mv square. This is gamma minus 1 mc square. This is how classical kinetic and relativistic kinetic energy can be written. And momentum, as we discussed earlier, it can also be described. So now yes, this is our conclusion of the lecture series of special theory of relativity. I hope you like the lecture series. So if you like it, then please subscribe. If you don't like it, then I will also be bringing more interesting segments, not just about physics. I will talk about day-to-day life stuff and all that. So be sure to subscribe to this channel. Thank you so much.